Hello, today we're going to be talking about the flame guard system that we created in mechatronics. The purpose of this project is basically to extinguish any fires or fire hazards. Now, the way it works is we created a vehicle that will basically monitor any surrounding flames. If it's towards the rear of the vehicle, it will turn around and then it will face the direction of the flame. There's a water nozzle directly in front of the vehicle, which it would be used to extinguish the flame hazards. And the purpose of this project is basically to create a system that will be applicable to places and industries where fire hazards are a real thing, such as airports, hospitals, and maybe even wildfires. So there's potentially a huge amount of possible utility with this device. And the purpose of this is just to strengthen our knowledge in electromechanical systems, enhance our engineering experiences, and integrate new systems and devices that we're unaware of and see how they can work for the point of our objective being to extinguish fire hazards. Okay, so we're going to go over the flow chart, the flow diagram of our code. So the first step of the flame guard program functions is to wait on standby until a flame is detected. If no flame is detected, it will remain on standby and will just remain stationary. Once a flame is detected, the IR sensors will then determine where the flame is located. So depending on if it's directly in front of it, it will rotate forward. If it's, let's say, towards the rear or towards the left or towards the right, it will rotate counterclockwise or clockwise until the front of the pump is directly in front of the flame. Once the pump has been rotated towards the flame, the vehicle will spin forward until a particular value is reached. If the value is, let's say, 700, it will rotate towards the flame until the 700 value is reached. It will stop, and then it will activate the pump, which will then extinguish the flame with the water from the tank reservoir.
So we're going to go ahead and do a quick overview of the code, starting here on line 1. So lines 1 through 2 we are defining how many sensors we have and on which pins on the Arduino they're located. So on analog pins A0 through A5, we have the first 5 IR sensors, and on digital pin 7, which we're treating as analog 7, we have the last IR sensor. Lines 4 and 5 declare the speed that we run the motors at and in which direction. And as you can see here on lines 7 through 13, pins 11, 12, and 13 control the left side motors, and pins 10, 9, and 8 control the right side motors. And digital pin number 7 controls the pump. So moving on to the setup, we are defining which pins are outputs. So in this case, which ones go to the motor controllers and to the transistor which controls the pump. And lastly, for our setup, we are initializing all of our sensors. So this little um, loop here goes through all of the sensors that we defined here at the beginning and initializes them and just prepares them to take, prepares the Arduino to take the signal that the IR sensors are generating. So the loop is where most of the work is being done. So these first 3 lines are just general setup values that define what the maximum value that the sensors are outputting and at what level that a flame is being detected. So here we can see is 900, and this we kind of just figured through trial and error, really, just how to calibrate the sensors. So this first loop here is just constantly cycling through all of the sensors and seeing if any has detected a flame. And then if a flame is detected and it's lower than this threshold value, then it sets that sensor to be active. So then that tells the microcontroller, hey, this sensor is detecting a flame. It's on this side of the car. So, and then this following section here just tells the Arduino to control the motors depending on which sensor has been active and on which side to turn the car. So starting here, if sensors 0, 1, and 2 have been activated, then that means it's on the left side, so then the car will turn left. If if sensors 4, 5, and 6 have been activated, then that means the fire is on the right and the car will turn to the right. In here, if sensor number 3 has been activated, um, notice it says 2 here. That's because the Arduino starts counting from 0. But if sensor number 3 has been activated, that means that the flame is centered in front of the car and to approach it. And then once it's a certain distance away, in this case, our intensity value is 690, which is approximately 2 to 3 inches away from the car. Then the car stops and it turns on the pump using this extinguish function, which you'll see later on in the code. And then it puts the flame out. So if none of these conditions have been met, then the car will just go forward because that means it knows a flame is there, but it's not close enough to activate it and reach with the pump. And if no flame has been detected at all, then nothing happens. The motors will not run and the pump will not be activated. Everything else from this point is just functions declaring how the motors work and how they should operate depending on all the values that have been set above. So here we have our move forward function, which just sends signals out to the motor controller telling it how to activate the motors, how fast to activate them, and which direction to activate them. So all of the functions that control motor control are pretty much structured in this way. So here you have the move forward, the turn left function, and the turn right function. And you can see the only real difference is in what direction that the motors are being turned. So in this case, um, these are turning left, these are turning right, and you can tell because of the inverted sign using the exclamation mark. Then we have the function that stops the motor. So this just deactivates the enabling pins so that the motors aren't being powered anymore. And lastly, we have our extinguish function. So this one works. This one actually is taking a parsed value from the max intensity readings that the sensors are outputting. And it's using this so that once this function has been called, it knows that once the intensity rises above this value, that means the fire has been put out and that to stop dispensing water. And after that's been met, then the function is stops being executed and then it goes back into the main loop. And it just constantly cycles through that depending on whether or not a flame has been detected.
So very briefly, I just want to go over the card itself and kind of show you an in-depth view of all its components and functions. So we have a removable lid, which is where the pump and the water reservoir is located. We then have the hose and the nozzle. This nozzle just helps us increase our pressure. Down here, you can actually see the 4 DC motors. And then we have 3 IR sensors to increase the view of field, the field of view. We have our prototype shield where everything is soldered on. We have our resistors, we have our transistors, we have the breadboard, which serves as the connection to all of our components. And then we have the microcontroller below the prototype shield. So this is like actually what's controlling the whole system right now. And then towards the back, this is actually where we have our battery pack. So we have the 9-volt over here. So the 9-volt is what powers the pump itself. And we have a 6-volt battery pack over here, which is what powers the sensors and the DC motors themselves. And due to that, we are limited to the amount of operation time. So yeah, that would be our in-depth view of the system itself. And I hope you enjoyed. So very briefly, as you can see, this is the integration steps for our project. The first step was integrating the microcontroller, which has all the inputs and outputs for the IR sensors, the pumps. It also contains connections to the battery packs. And after we installed the microcontroller, we then move forward into the DC motor integration. So we installed the DC motors, which controls the torque output on the wheels. And we then worked on the code to basically allow the wheels to rotate accordingly to the IR sensor's value. So we worked on basically allowing the vehicle to move towards the flame hazard. After we included the DC motor integration, we would then work on the final motor integration, which was the water exhaust integration, so the water pump, and that was our last step. So after all of the code worked with the vehicle, detecting the flames and moving towards the flames accordingly, we then integrated the water pump, and we simply just added the final bits of code um, to basically produce mass flow of water towards the fire hazard. Just gonna pretend like I put that down. Oh,
Immediately.
yeah, wait, hold up. To conclude the project, as you can see, we had some troubles with the testing, but the overall objective of the flame guard system was achieved. Something that we can work on and something future teams can work on is increasing the scale model of this vehicle. As you can see, a miniature model doesn't serve too much as a safety solution. Integrating a mist nozzle to increase our target zone for the fire hazard would beneficially increase the utility of the project. And overall, just increasing the system reliability is our main issue. So just making sure that this system works 100% of the time, just because even one moment of failure would result in disastrous results for whatever industry or for whatever area that this system is covering for fire hazards. We're also having an issue with reduced daylight, with daylight interferences. I'm sorry. So we're getting interferences from daylight. So we need to recalibrate, or we need to purchase better quality of sensors in order to reduce that daylight interference that we were encountering. We needed to improve the motor performances. So there's a lot of mass, as you may know. Water weighs quite a bit. So improving the motor performances will greatly increase the utility and efficiency of the system. And overall, it's just increasing the efficiency of the system by maybe introducing better battery packs, better DC motors, better water pumps. Also, including better electromechanical systems. As you may know, Arduino might not be the ideal route for the supplier of this project, but it's what we had, and I believe that the overall objective of this project was achieved. So, me and my team are very happy with the results. To conclude this project, we would just like to give a special thanks to Dr. Khan and all of his guidance and feedback during this time working in the project. He helped out immensely with the Simulink analysis. He helped us determine some faulty errors in our project. And overall, he motivated us to just increase the utility with his lectures. All of our knowledge was gained from his lecture slides, and special thanks to him. We couldn't have done it without him. So thank you, Dr. Khan, for all your great work. And lastly, we would like to thank the Gaia Lab for allowing us to use their 3D printers. So it wouldn't have been possible to manufacture that water tank and water reservoir, that water nozzle, if it wasn't for the Gaia Lab. So special thanks to all of them for working with us, and especially in these under these time constraints. So thank you, and that would be our flame guard presentation. Thank you for listening, and I hope you enjoyed.